At first glance, it looks almost like a typo, a sort of mathematical optical illusion. But it is completely real, mathematically proven, and actually incredibly useful in the real world. Say hello to the inverse quadratic formula. X1 and 2 equals 2c divided by negative b, plus or minus the square root of b squared minus 4ac. If this sounds completely alien to you, it's probably because we all remember a very different high school math class. We remember the teacher standing by the whiteboard, writing down the classic formula we memorized until it was ingrained in our brains like a nursery rhyme. X1 and 2 equals negative b, plus or minus the square root of b squared minus 4ac, all divided by 2a. Most of us accepted that original formula as absolute truth without asking too many questions. But what if I told you that this alternative mathematical secret has been hiding in plain sight all these years? If you pay close attention to this inverse formula, you'll notice something weird happened here. The numerator and the denominator simply flipped. The familiar 2a completely disappeared from the bottom of the fraction, and in its place 2c suddenly popped up on top in the numerator. How does that even make sense? How can you flip a formula on its head and still get the exact same answers? Let's dive in step by step and discover the magic behind the numbers. To understand how we actually arrive at this formula, we need to use an ancient and clever algebraic trick called multiplying by the conjugate. It is a trick mathematicians love to use. We start with the classic formula we know. Now we take both the numerator and the denominator and multiply them by the conjugate expression of the numerator. What does that mean? It means we take the exact same numerator we have now, but we just flip the plus minus sign in the middle to a minus plus. So our new expression is negative b minus or plus the square root of b squared minus 4ac. When we do this up top in the numerator, we create a classic situation of a plus b times a minus b. For those who remember, this is exactly the famous shortcut formula for the difference of squares. The result of this beautiful multiplication leaves us with b squared, minus the entire expression inside the square root, meaning minus b squared minus 4ac. Now a magic of cancellation happens here. The b squared completely cancels out with the second b squared. The minus sign before the parentheses turns the minus 4ac into a positive. And at the end of all this mess, we are left up top simply with a clean and tidy 4c. Down below in the denominator, the story is much simpler. We just multiply our original 2a by the new conjugate expression we added. So we get 2a times that whole long expression of negative b minus, or plus the square root of b squared minus 4ac. Now, to finish our transformation and combine the numerator and denominator into one new equation, all that is left to do is cancel out the 2a that is present both on top and on the bottom. And that is it. What did we get? Our inverse magic formula. X equals 2c divided by negative b minus or plus the square root of b squared minus 4ac. And by the way, if the fact that it now says minus or plus instead of plus or minus stresses you out, don't worry. It just means we still have two possible answers. They will just arrive in the reverse order. For the final calculation, it really doesn't matter. The theory is nice. The question is, does it actually work in practice? Let's take a simple equation that is easy to solve and test it out. Let's take the equation, x squared minus 5x plus 6 equals 0. In this equation, our numbers are simple. A equals 1, b equals negative 5, and c equals 6. If we take the high road and use the classic formula, x equals 5 plus or minus the square root of 25 minus 24, and all that divided by 2. The calculation inside the root gives us 1, so it becomes 5 plus or minus 1 divided by 2. The first solution is 6 divided by 2, which is 3, and the second solution is 4 divided by 2, which is 2. Easy and simple. Now let's challenge the system and use the new formula. X equals 2 times 6 divided by 5 plus or minus the square root of 25 minus 24. This immediately equals 12 in the numerator, divided by 5 plus or minus 1 in the denominator. Let's solve. If we use the minus in the denominator, we get 12 divided by 4, which is 3. The first solution works. And if we use the plus in the denominator, we get 12 divided by 6, which is 2. The second solution works as well. Both methods work like a charm and lead to the exact same destination. So now you are probably sitting there asking yourself, if it works so well and it is so elegant, why do math teachers around the world keep this formula an absolute secret? Why doesn't the Board of Education put it in textbooks? This is exactly where we hit the trap and the reason why this formula can be dangerous. Have you ever asked yourself what happens when the entire bottom part of the fraction, the denominator, zeroes out? After all, the first rule you learn in math is that you are not allowed to divide by 0. Division by 0 is a catastrophic event that breaks the rules of arithmetic. If we investigate this a bit, we will discover that our denominator equals 0 only when c equals 0. What does this mean in practice? Let's see this collapse happen in real time with a simple equation like x squared minus 3x equals 0. In this case, our c is 0. The solutions are obvious to everyone almost immediately without calculating. X can be 0 or x can be 3. But what happens if we are stubborn and plug it into our inverse formula? In the numerator, we will get 2 times 0, which gives us 0. In the denominator, we will get 3 plus or minus 3. For the first answer, everything looks fine. we will get 0 divided by 6, which gives 0. For the first answer, everything looks fine. We will get 0 divided by 6, which gives 0. But hold on tight for the second answer. We will get 0 divided by 3 minus 3. Meaning we just divided 0 by 0, we got an expression that is completely meaningless. The equation just collapsed in on itself, and that is exactly the answer. The classic formula they teach us in school is a reliable workhorse. It always works stably and safely. The new inverse formula, on the other hand, fails embarrassingly every time one of the solutions to the equation is exactly 0. But just before we throw the inverse formula in the trash, there is one group of people who actually really love it: programmers and computer scientists. The problem in the computer world is that a computer has limited physical memory, so it can only store a limited number of digits for every number. When a computer takes two massive numbers that are almost identical and subtracts them from one another, most of the large leftmost digits cancel each other out. What is left is only a tiny remainder at the end that is full of small rounding errors. This destructive phenomenon is called catastrophic cancellation. In the quadratic formula, imagine a situation where the parameter b is a large positive number, say 1,000, and the 4c part is a tiny number. The result of everything inside the square root will be almost 1,000. Let's say 999.99. If we use the classic formula to find the solution with the plus, we will take negative 1,000 and add that 999 to it. We essentially just subtracted two giant numbers that are almost equal in size, and here the computer loses most of its precision and spits out a fake inaccurate result. If instead we calculated the solution with the minus, we would get negative 1,000 minus 999. In this case, we are actually adding two large negative numbers together. There is no catastrophic cancellation here, and the computer's precision is maintained perfectly. This is called the safe calculation. But wait, if you think about it deeply, something here doesn't add up. After all, the dangerous expression located in the numerator of the classic formula is the exact same expression located in the denominator of the inverse formula. So if calculators simply threw away the regular formula and only used the new one, the computer would still run into the exact same collision when trying to calculate both solutions. Except this time, the collision would happen down below in the denominator instead of up top in the numerator. We haven't solved anything here, so how does this actually help? This is where the real algorithmic trick kicks in. The secret is that the computer doesn't pick one formula and throw away the other. Instead, it combines both of them to solve the same equation. Let's break it down. Instead of rushing to do both calculations, both the dangerous one and the safe one, the computer checks in advance which one is the safe calculation. It performs only that one and skips the dangerous calculation completely. Now, to find the first solution, the computer takes this safe calculation, plugs it into the numerator of the classic formula, and divides by 2a. That is how we get a completely precise first solution. And what about the second solution? The one that was supposed to use the dangerous calculation to be found. Here comes the magic. The computer takes that exact same safe calculation result it already produced, but this time it plugs it into the denominator of the inverse formula and divides 2c by this result. Because the inverse formula outputs the answers in reverse order, plugging the safe number into its denominator generates the exact solution we were supposed to get from the dangerous calculation. Without ever actually doing it, the computer performs the root and addition calculation only once exclusively for the safe version. Then it uses this result twice, once up in the numerator of the regular formula, and a second time down in the denominator of the inverse formula. This is how it manages to extract both solutions at maximum precision without performing even a single problematic subtraction along the way. Math, it turns out, isn't just about knowing the formulas, but knowing how to cleverly use them both together. If this changed how you look at equations and you're curious about what other mathematical tricks are hiding in plain sight, click subscribe and let's figure them out together.